Good afternoon, everyone. So I'm very happy today to share our recent work about Mega. So Mega is an efficient attention mechanism, and which has been accepted to this year's year. And this is the joint work with my co-authors from USC, Meta AI, CMU, and SGTU. So during my talk, please feel free to interrupt me if you have any questions. Okay, let's start. So we know that designing like a single and unified like neural architecture to capture like the sequential dependencies in data is a central and challenging problem in the task of sequence modeling. And in the past 5 to 6 years, the transformer architecture has with the attention mechanism has been the dominant model for its like impressive successes in a wide range of like applications and data modalities, including like language, image, audio, and videos, right? So, but we know that the transformer is still not perfect, and there are like at least 2 well-known like limitations in the design of the attention mechanism. And first, we know that the inductive bias in the attention mechanism is weak. And this is because the attention mechanism assumes like almost no prior knowledge about the dependency patterns in the data. And for example, for the positional information in transformer, it is only from the like the absolute or relative positional embeddings. And the second issue is the time and space complexity. So in attention, the complexity is quadratic with respect to the sequence length. Here, like the age is the number of heads, which is also a large value in practice. So this kind of quadratic complexity makes it like expensive for long input sequences. And so as we mentioned, the concept of inductive bias. So let's first discuss like what is inductive bias. So by comparing attention with other neural architectures, we know that convolutional neural network applies a kernel to like model contextual information within a small local window. So therefore, there are at least 2 straightforward inductive biases in CNN. The first is it focuses on only local dependencies, and the local window or receptive field is usually small. So in practice, we use like the window size equals to like 3 or 5. And second, the kernel is like time and input invariant. So in CNN, the kernels are just some like model parameters, which are independent with the input data and the time step. And for the recurrent neural networks, the inductive bias is different from CNN. So the RNN recurrently model the dependencies of input tokens step by step, and the recurrent format is time invariant as well. And we see that for both CNN and RNN, their inductive biases are clear and strong, and these biases in practice sometimes significantly facilitates the learning of certain types of data dependencies. For example, the CNN has been widely used in modeling like the dependencies in image in the pixel space of images, and RNN has been applied to modeling like time series data and also like sequential data. Okay, so but on the other hand, the attention mechanism does not assume like prior knowledge about the dependency patterns. It assumes that we can directly learn all the types of the pairwise dependent patterns directly from data. But in practice, usually it is hard because sometimes this kind of dependencies are complex, and if the sequence is long, then it is a challenging task. And recent study has shown that transformer is neither accurate nor efficient for long sequence modeling, and we need to resolve this issue by some more advanced mechanism. So to address the weak inductive pairs and the quadratic complexity of transformer, so we propose the MEGA architecture. So here is a brief summary of MEGA. So basically, MEGA is effective and efficient architecture for long sequence modeling, and it has achieved outstanding performance on various types of data. And one key insight of MEGA is to incorporate the classic exponential moving average approach into the attention mechanism. And also, we further propose the MEGA chunk, which is an efficient variant of the original full version of MEGA, and it reduces the time and space complexity from quadratic to linear. So in the following sessions, I will introduce the key components of MEGA. So the first is the EMA module, which incorporates stronger inductive pairs into attention. So and the second part is a single head gated attention. So where we add a reset gate to the attention output. So more importantly, we theoretically prove that by adding this gate, the single head attention is as expressive as multi-head ones. So in practice, we do not need to suffer from the multi-head attention. And at last, I will introduce MEGA chunk, which is an efficient variant of MEGA. So let's begin with the EMA module. So to simplify the introduction, so let's first assume that our input X is a sequence of one-dimensional scalar. So here we assume X is a sequence of X1, X2 to Xn, and for each t, at each time step t, xt is just a scalar. It's a one-dimensional scalar. And so at each step, we see that EMA just averages the input value X with weight decaying over time. So here alpha is the decay factor. And we see if we have higher alpha, then we just discount the previous observations faster, right? And also EMA plays a strong inductive pairs. That is, the dependency weight between two tokens decreases exponentially over time, and it is also input agnostic, which means it doesn't depend on the input data. And one limitation of the classic EMA is that the weight of the current and previous observation are coupled, and a straightforward extension is to introduce a damping factor delta to reflect the coupled weights. And in MEGA, both the alpha and delta are just some learnable parameters. And to further improve the expressiveness of EMA, we introduce a multi-dimensional variant of EMA. So the idea is pretty simple. So now suppose we still assume the xt is a one-dimensional scalar, and we first expand xt to h dimensions via a vector beta. And then we apply like EMA individually to each dimension to get the h-dimensional hidden state HT. And then we use another vector to map the hidden state HT back to like a one-dimensional output. And by this way, we can just have like a more expressive EMA module. Okay, so now we have seen the basic format of EMA, but the next question is how could we compute EMA efficiently, right? So from the definition of EMA, so it seems that we need to compute the output YT in a sequential way, like the recurrent neural network, right? So, but we know sequential computation will be like very slow for long sequences, and this is why like recurrent neural network is rarely applied to modeling long sequences. But fortunately, there exists like efficient algorithm to compute the output tokens of EMA in parallel. And the key insight is that the EMA weights are input independent. So we see that for each token, the weight, for example, for the token YT-1, its dependency weight of other tokens are dependent with the input X. So it means at each step we can compute these weights in advance, and once the weights has been computed, we can apply like a convolution transform with the sequence with the kernel in a sequence length kernel, and then we leverage the fast Fourier transform to efficiently compute all the output YT. So this way, we do not need to compute YT one by one. We can compute all the outputs in a parallel way. So this is why like EMA is much more efficient than the traditional like recurrent neural networks. And so here, if you are familiar with state space model, then you can see there is like clear connections between EMA and the state space model. So technically, state space model is like defines like a continuous, defines a sequential model in the continuous time space, and it assumes like the dynamics of the hidden state is a linear combination of the previous hidden state and the current input. So here the T is the continuous time step, and A, B, C are some learnable parameters. And here I just briefly list the comparison between S4 and our EMA. So S4 is probably one of the most popular state space model which has been applied to discrete sequence modeling. So in S4, the matrix A is a complex and low rank metric, and it is defined in the continuous time space. And since we want to apply the S4 or other state space models to model like discrete sequence data, so we need a step called like time step discretization to convert the continuous time space back to the discrete time space. And in S4, they apply like the bilinear method. And also, to make S4 work in practice, it requires some like advanced initialization method. And in S4, they use the hippo initialization, which has been proposed like 4 years ago. And for EMA, the formulation is much more simpler. So for the parameterization, alpha is just a real value diagonal matrix with elements in a range from 0 to 1. And it is defined in the discrete time space. So we do not need to do any kind of method to do the time-step discretization, and our initialization is just simple. We just use sample from the Gaussian distributions, so it does not rely on advanced initialization methods. And so far we have used like one-dimensional input X as a running example, but how to expand EMA to like a sequence of vectors, right? In practice, our input is a sequence of embeddings. And the idea is straightforward. We just stack the individual EMA layers, one for each dimension. And since these layers are independent, so there are no interactions across the dimensions of the output Y. But we can just add like a linear transform, linear layer like after each EMA layer to incorporate back the interactions across the different dimensions in practice. And so in practice, we do not need to really stack and like the EMA layers. We can implement the EMA module aware vectorization using the packages like PyTorch or TensorFlow or JAX. So the implementation is easy. Okay. So so here is the summary of EMA layer. So technically, it incorporates strong inductive pairs and much more efficient to compute than attention and traditional RN layer. So now let's move forward to the single head gated attention layer in Mega. And so here, first, this is the attention function used in Mega. It maps the query key and value vectors into the output vectors. And our attention function also adds like a relative positional pairs because we do not use any positional embedding in our architecture. And the idea of adding a gate to the attention output has been proposed in previous works. And so concretely, we just introduce a reset gate gamma. And here gamma is practice, it's a transform of the input X. For example, we can use multi-layer perception to model the gate gamma. And then the gamma is like directly applied to the attention output. So here the dot product means like the element-wise multiplication. And previous studies have shown that by adding this gate, single head attention can achieve like comparable performance with multi-head ones. And in our paper, we provide a theoretical support for this observation. And we show that if we assume the transform like gamma is a universal function approximator, then for each input X, and we can always find like a solution with the gated attention, single head gated attention that equals to the output of a multi-head attention. So with this theorem, we can see that if our reset gate is strong enough, then we do not need to use any multi-head attention. Just a single gate is it's sufficient. So that is why in our Mega architecture, we always use gated attention with single head. And here I just omit the proof details. And if you are interested, you can just read our paper. The proofs are provided in the appendix. And so this slide displays the architecture details of Mega. So we see that we also introduce another gate phi along with gamma, and this gate is similar to the update gate in GRU, and is used for gated residual connection for the output. And here I will not go into more details about the architecture design. And if you are interested for the details of the architecture, you can go to see our paper. Okay, so so far we have focused on introducing stronger inductive pairs into the attention mechanism, which but now the model, like the mega model, still has the quadratic computational complexity, right? Even though it is only a single head attention, but the from the complexity perspective, it is still quadratic with respect to the length of the input. So next, we will see how could we reduce the complexity to linear by megachunk. And the motivation of megachunk is very straightforward. So we just split the input sequences into multiple chunks with fixed lengths. And here, there are no overlaps between successive chunks. So all the chunks are entirely independent. And then we apply the attention mechanism within each chunk. So we see obviously if the chunk size is fixed, then the complexity is just linear. And also it is very easy to implement because there are no overlaps. Between chunks. It doesn't. So the implementation is easier than sliding the sliding window based chunk attention long former. So here in our case the implementation is easy. But one issue of this chunk based attention is that we just lose the contextual information between chunks. But in Mega, this is not a problem because we have the EMA module, which preserves the information across different chunks. So here is the diagram to illustrate the largest possible dependency length captured by a Mega chunk layer. So we see that even though the attention is applied within a chunk, but the EMA layer is able to capture the contextual information across the chunk boundary. So the overall architecture is still able to capture the dependencies across the whole input sequence. Okay. So this is just the idea of mega chunk. Okay, so far I have introduced the architecture design of Mega, and let's move forward to the experiments part. So in our paper, we evaluated Mega on 5 benchmark tasks across different types of data, including long-range arena, machine translation, language modeling, ImageNet classification, and also raw speech classification. So this table just summarize some of our main results. We see that on the first 4 tasks, Mega outperforms Transformer and S4. And on raw speech classification, Mega is slightly worse than S4, but it's still much better than Transformer. And so we further conduct analysis on the long-range arena benchmarks. So for those who are not familiar with this benchmark, so long-range arena just consists of 6 long sequence classification tasks, like 3 for text and 3 for images. And to intentionally make the sequence longer and to make the task more challenging, RA just use sequence of bits as input for text and sequence of pixels for images. And we see that for the longest one, Pathfinder X, the input sequence is more than 16,000 of pixels. And also this task is challenging because this task is to ask the model to classify like if there is a path between two ends in the image, and the model needs to first like detect where are the two ends, and then to classify like if there is like a path between these two ends. So this is a challenging task. And here we list the model performance, and we see that on all the six tasks, like Mega is much better than previous models, including transformer and some efficient attention mechanisms, and also the S4 model. And especially on the task of Pathfinder X, so we see that Mega achieves like nearly 98% accuracy, and this is the first attention-based method which is able to achieve like accuracy better than random on this task. For other attention-based method, all the models just failed on this task. And also in terms of efficiency, we see that Mega is around like 3 times faster and use than 1/3 of the memory than transformer. Excuse me. And this is mainly because Mega use like single head attention, which like saves like a lot of computational resources. And for Mega Chunk, we can further improve the efficiency with like minimal quality loss. And we also analyzed the impact of chunk size for the Mega Chunk model. And here we use 2 tasks from IRA. One is IMDb, like byte level text classification, and second is like the pixel level image classification on Cepher 10. And we see that we see some interesting observations. So for the text classification, Mega Chunk is able to obtain like near 90% of the accuracy, even with a very small chunk size, like 16. So it's like the performance almost there are almost no performance loss by decreasing the chunk size. But for image classification, so we see that the chunk size is still very important. So it means like for pixel level image classification, we still need the attention to compute some like global dependencies. And we also did some like evaluation studies to gain some more more insights of Mega. So first, we want to test like if we can further improve performance if we replace EMA with like more advanced state space model like S4, S4D. And based on our experiments, there are no significant improvements if we replace like EMA with S4. And sometimes even like this kind of replacement may lead to some like unstable training. So it means it is still an open question to integrate these 2 types of models into one architecture. So it can be an interesting future direction. And also, we just test the importance of the damping factor in the EMA. And we found like it is important to some extension, and without the damping factor, like we see a consistent drop of performance by around like 2 points on the LRA tasks. And also we found like the relative positional bias is also important, especially for the image classification task of EMA in the LRA. So on text classification task, we only see a slight decrease of performance, but for image classification, if we remove the relative positional bias, then we see like a drop of around 20 points accuracy. So it means the relative positional bias is important for image classification task. And here I also summarize some like possible future directions. So first, we will continue accelerating the speed of attention and Fourier transformation with like more advanced CUDA kernel. I know like recently there are some progress in this direction from the Stanford University. They just implement a faster kernel for the FFT. So it makes the model even faster. And also we want to apply our Mega to some large scale pre-training task with longer context. And we have recently we have trained like we have applied Mega to multilingual like the multilingual BART experiments. And but you know, pre-training is expensive, and based on our current results, with like 1/10 of the training steps, Mega is able to achieve like the similar performance with multilingual BART. So it's promising. It means like Mega is it converges much faster, and like also it at each step it's much cheaper, right? And also we want to apply like Mega to some multi-modality task, but there are still some like issues on the direction, because you know, in our experiments, even though Mega achieves like promising results on different types of data, but there are still some architectural dependencies between these models. So for example, on different tasks in our experiments, we use different normalization types. We found like on languages, layer normalization usually works best, but on images or audios, batch normalization is still the best. So it means like if we want to propose a unified model, we need to reserve these dependencies for normalization types. And also we found like the attention activation functions is also different for different models, for different types of data. So for example, in our paper, we do some ablation study to show that on languages or texts, softmax attention is still the best, but on images or audios, like our like the element-wise attention activations, for example, the ReLU 2 or the new proposal like a function based on Laplace function is better than softmax. So in practice, if we want to unify them together, we need to find like a attention activation function which works well for all the types of data. And yeah, so this is just a summary of this talk. So we introduced Mega, and also we release our code together with our checkpoints on this GitHub. So yeah, so I think I can stop here.